Hello, everyone. Welcome to ConnectCon, presented by FTC Team 9794, Wizards.exe. Join us on our last day of our magical journey where you can hear from STEM professionals from Google, APL, iRobot, and more. My name is Ronak Banerjee, and I'll be your host for this session. Please use the chat for any questions related to the presentation, and we'll address them at the end. Today, we're honored to have Dr. Alycia Weinberger speak about potentially habitable planets and how to find them. As an aspiring astronomer and astrophysicist myself, I'm certain that I will find this interesting, and I hope all of you do too. Dr. Weinberger is an astronomer for the Carnegie Institute for Sciences Earth and Planets Laboratory. Today, she will show us how astronomers study planet formation using some of the largest telescopes on Earth. Thank you, Dr. Weinberger, for taking the time to present at ConnectCon. And without further ado, let us begin.
Thanks. It's my pleasure to be with you today and to share with you some of the excitement of what we can do in astronomy and especially for how we understand exosolar planets. So I hope that you have always wondered alongside me, are there other planets like Earth in our galaxy? And Earth is so special and so beautiful, which I always like to look at it in this photograph. This is a kind of updated version of the one the Apollo astronauts took, taken by a mission that the Japanese Space Agency launched to the moon, but really puts in perspective how we are a pale blue dot floating in a vast sea of space. And in order to understand how we came to have this precious planet that was capable of supporting life and intelligent life, at least most of the time I think we're intelligent life, then we need to look to how these planets form and whether we can actually find more that are like our own. So you may have heard of the Kepler space mission, which was a NASA mission that spent about 5 years searching for planets around other stars. And it searched for them using what we call the transit method. So it looks for planets as they pass between us and the other star, in which case they make their star a little bit dimmer. They block a little bit of the light coming from their star to us. So here's a movie of about 5,000 planets that the Kepler spacecraft found. Actually, this is just the subset of those 5,000 in which there's more than one planet around each star. So there are a few really important things, and this movie is going to loop. So there are a few really important things to look at. One is that our solar system is drawn on here for scale. So Mercury, Venus, Earth, and Mars are these 4 planets right in here. And you can see Jupiter right here. So dots about this size and this color are the size of Jupiter and the temperature of Jupiter. So that blue is pretty cold. Jupiter is only about 250 Kelvin, 250 degrees above absolute zero. So if you can find the Earth in there, it's not really that much warmer. It's about 350 Kelvin. That's the temperature of everything around us. But look at how hot and red some of these planets are. They're almost the temperature of lava, 1,000 degrees. And that's because they are so close to their stars that they're just getting blasted by the radiation. It's as if they never get out of a really sunny day. So they orbit so close to their stars that they're incredibly hot. So most of these planets that you can see are orbiting their stars closer to the stars than Mercury orbits to our sun. These are incredibly small planetary systems that really don't look much like ours at all. On the other hand, you can see that there are some similarities between the planets that were found by this mission and our solar system. So there are a range of sizes of planets, and they range all the way down to the size of Earth, these small dots, and all the way up to planets that are bigger than Jupiter, these very big dots. So a vast panoply of planets exists, a huge variety, both in size and in temperature. And what we want to do is try to tease out, are there other planets that really are like Earth? Are there other solar systems that are actually like our solar system? And what are those planets made out of? Because to be habitable, you might want to be the temperature of Earth, but you also want to have some of the really important things that Earth has to support life, like water, for example. So here's another way of looking at all of the planets that have been found so far by that Kepler mission that I just showed you, but also by all the other ways that people have looked for planets. And this is a plot that shows how big the planet is and how close or how fast it goes around its star. And so the faster you go around your star, the closer you are to the star and the hotter you are. So here's Earth. We go around our star in 365 days. And everything on here is relative to the size of Earth. So we're one Earth size, right? And Venus is just a little bit smaller than us and just really a little bit closer to our sun than us, if you look at it in the context of this plot of all the planets we know. And yet Venus is not a habitable planet, right? It's hot, it's inhospitable, it has an atmosphere of carbon dioxide and sulfuric acid clouds. Its temperature is enough to melt the spacecraft that we send there. So even though Venus is in many ways extremely similar to Earth, it's not a habitable planet. So now you can see that we haven't quite found an Earth 2.0 in terms of how far it is from its star, how fast it orbits its star, and how big it is. And the fact that the planets that you see are all closer to their stars and bigger than Earth is mainly because we just don't have the technology yet to find the smaller ones that are further away. It's easier to find planets if they orbit their stars frequently. They go in front of the star many times, and so you have many times to catch that. It's easier to find them if they're bigger because they tug on their stars more or they block more of the star's light. And so a lot of the progress in finding exoplanets in the next several years is pushing our detection limits to get better and better so that we can find the planets that are the size of Earth as far away from the sun as the Earth is from the sun, far away from their stars as the Earth is from the sun. But the exciting thing is lots of people have found planets smaller than the Earth, right, down here. And so people have tried to estimate how many, based on what we did find, how many Earth-like planets in terms of their size and their temperature might there be in the galaxy. And the estimates range from about 10% of stars might have an Earth-like planet to 25% of stars might have an Earth-like planet. And if you think about the fact that there are 100 billion stars in the galaxy, that is still a lot of planets that could be the same size and the temperature of Earth out there. So it's our job as astronomers to push those detection limits so that we can hopefully find those in the not too distant future. So in that way, the solar system doesn't seem rare. But remember that just if we find a planet that just is the same temperature and the same size as the Earth, that won't tell us if it's truly habitable. And the similarity in size and temperature between Venus and Earth, or size and location between Venus and Earth, tells us that there's a lot more that goes into making a planet habitable than just how big it is. And so it's important to ask the question of how did the Earth come to be so habitable? Like, is there something special about us, or what do we know about our history? So for one thing, we live in a solar system that has a very nice structure to it. And you've probably seen in the news sometimes when all the planets line up. This is something that makes astrologers all excited. And astronomers say, well, the planets are always lined up. You just can't always see them all at once. But this is a beautiful picture from the astronomy picture of the day taken at the observatory I work at in Chile, and which is also forming the backdrop of my Zoom call here today, Las Campanas Observatory. Of a time when you happen to be able to see 3 of the planets at once, and they all line up on what we call the ecliptic. So you can imagine the planets of our solar system are beads rolling around on a plate, and they never go far above the plate or below the plate. They roll around on this plane. And so sometimes they all happen to be on one side of the sun, and we can see them all at nighttime, and at other times they're spread out on different sides of the sun, so we can't all see them at once at nighttime. Jupiter and Saturn, by the way, are up at the beginning of the night now, and they're so beautiful and bright. Practically the brightest thing in the sky that you can see right now is Jupiter. If you look toward the southeast at nightfall, you'll see Jupiter very bright, and then Saturn just a little bit further east of it, also gorgeous. And if you have a small telescope, I took mine out a couple of weeks ago, they both looked just gorgeous. So we have this very regular solar system where all the planets are lined up. And actually that's also true of all those planetary systems that you saw spinning around discovered by Kepler, because Kepler wouldn't have found them if they weren't like that, if they weren't lined up. But we still don't know if there are many planetary systems that Kepler missed because they aren't lined up the way ours are. Now we also have this big planet, Jupiter, which is further away from our sun than we are. And that helps to protect us. It's kind of like the giant vacuum cleaner of the outer solar system. So if comets come into the solar system, most of them get perturbed out of the way by Jupiter. So that might be important, because really what sets the history of a planet is how it formed. So we have to think about our history and what the history might have to be for any other planets that we think might be habitable. So our solar system is 4.567 billion years old, 4.5 billion years. That's a really long time and very hard to think about. And we know that number extremely precisely because we can measure the ages of meteorites, of the original building blocks that were present in our solar system in asteroids and which have fallen to Earth. We also know that the planets in our solar system were all formed by about 100 million years after the sun formed. So that's pretty fast, right? The first 100 million years, and we're 4.5 billion years now. So all the planet formation happened super quickly. But then there was this very long period of time between about 100 million years after the sun formed and now, when we still have evolved. The solar system has changed. And the biggest way in which it's changed is that the asteroids and comets that were left over from the initial building of the planets have been dispersed. They've either crashed into planets or they've been ejected, basically, by Jupiter. Those are the choices. So what do those small bodies, those asteroids and comets, do for us, right? They are the building blocks of planets. So probably the Earth started forming when asteroids stuck together, and then more asteroids came and stuck onto them, and yet more, until we built up things that were pretty big, like the size of Mars. And then those started smashing together, and they built things that were the size of Earth. And then if you got really big, when you were young enough in the solar system, like Jupiter, then you could start to suck in gas and form a gas giant planet. But if you didn't get big fast enough, then the gas goes away and you stay a mostly rocky or icy planet and not a gas giant planet. And so all of that had to happen super quickly. We think the gas went away in only about 5 or 10 million years. And then the rocks stayed around longer. So the question is this history, which resulted in our planet being the right temperature, the right size, and the right composition, having water and carbon and nitrogen and oxygen, things necessary for life, is that something that happens universally, or is that something special? So these collisions are what we're going to talk about for the next few minutes. So this is an artist's conception of what a giant collision might look like. This, for example, might be a collision that would produce the moon. We think that our moon was produced when something pretty big smacked into the Earth and created a lot of rubble and debris that then came back together under gravity and formed the moon. So these collisions can obviously be bad, right? We know that about 65 million years ago, these giant dinosaurs were wiped out on the surface of the Earth by a giant collision. And a lot of astronomers spend time looking for the other near-Earth objects that could produce an impact that could kill the current dominant species of the Earth, which we wouldn't like very much. So collisions can certainly be bad, but collisions help bring to the Earth also the materials that we need to develop life, and primarily amongst them water. So right now we do have a lot of small bodies in our solar system still. We call them generally the asteroids and the comets. And that on this diagram, you can see all of the currently known asteroids in our solar system. And you also see the orbits of Mercury, Venus, Earth, and Mars. So all the asteroids in red on here are ones that come into the vicinity of the Earth. So we call those the near Earth asteroids. Those are the ones that we worry about for impacts like the ones that killed the dinosaurs. The green ones happily stay out in the main asteroid belt, and we don't worry about them, but we do study them because they are the oldest materials in the some of the oldest materials in the solar system. And so they show us what those original building blocks of the planets look like. But they're very dry, and they have very little carbon. And so it's actually very hard to understand how this population of asteroids was the population that produced something which today looks like the Earth. So one possibility is that the asteroids that went into making the Earth aren't there to look at today because they went into making the Earth, and therefore we don't have a sample of them. We don't think that's exactly the right answer because the asteroids have been pretty mixed up over time by the planets. And so we think we have a fairly representative sample of the kinds of materials that were in the solar system early on. But it is a possibility. The other possibility is that we got some of our material from stuff that came from further out in the solar system. And today, further out in the solar system, we have the Kuiper Belt. And those are all the objects that are in red on this plot. So those are also sometimes called Plutinos or trans-Neptunian objects. They're the things that are in the outer solar system. And they tend to have, in addition to rock, like the asteroids, a lot of ice. And so if these objects came into the inner solar system early in our history and were part of the building blocks of Earth, they would have brought with them a lot more water and carbon and the other things that we need to sustain life. So they may have been moving through the solar system the whole time that the Earth was forming and provided us with some of the materials that we needed. So I should also say that on this plot, the inner solar system is tiny, so you don't see it. And what you're seeing here are Jupiter, Saturn, Uranus, and Neptune. And you can see there are lots of these Kuiper Belt objects, but not nearly so many, right, as the asteroids. And that's because over time, Jupiter has really and the other giant planets have depopulated our outer solar system. So we actually don't have so many comets left. So we do still have dust in our solar system too, that's made from the evaporation and the collisions of these comets and asteroids. So sometimes the comets come in close to the sun and the sun heats them up and causes them to fall apart and they create dust. Sometimes asteroids hit each other and they produce dust in collisions. And so if you go out on a very dark night and you look toward the horizon, usually when I've seen it best is before sunrise in the morning, you can see a disk of light that's called the Zodiacal Light. So here's the galaxy. These are all the stars in our galaxy, the 100 billion stars, of which 10 or 20% might have planets like the Earth. But this is the dust in our solar system that, you know how if you shake a blanket in front of a window on a sunny day, you'll see the dust glinting, at least the blankets in my house have enough dust that you'll see them glinting in the sunlight. Well, that's what this dust is doing, the dust produced by comets and asteroids. And it can be quite bright, even though there isn't very much of it, because each little dust grain is reflecting sunlight from the sun that's below the horizon. So you're not seeing the sun directly, but each of those dust grains is acting as a mirror to reflect light back to us. And the two things that would be most observable about our solar system, if another planet nearby had the same technology that we do today, the two things that they'd be able to find most easily about our solar system that would tell them that our solar system had created planets is the Zodiacal Light, because even though it's a tiny, tiny fraction, 1/10 billionth of the mass of the planets, It's so bright because it's made up of all those little dust particles. So we're able to see zodiacal light around other stars, or about maybe 10 times as bright if we could find it around other stars. And they'd be able to find Jupiter. And if they were patient enough, they'd be able to find Saturn using the same planet finding techniques that we have today. So the zodiacal light is what I like to think of as a fingerprint of a planetary system. It says that that star system made at least comets and asteroids that can produce dust, if not larger planets. So can we find this evidence of planets in formation, from the building blocks around other stars? Like, we found the planets themselves, but can we find the building blocks? Oh, I was going to say that collisions still happen in our solar system today. I don't know if any of you know about the 1994 collision of Shoemaker-Levy 9, which was a comet that got stripped apart by its first pass with Jupiter and then came back a year later and smacked into Jupiter and made these clouds on Jupiter. So I took these images when I was a graduate student. And since then, there have been a couple of more impacts of comets seen on Jupiter. So collisions do still happen today, although they're pretty rare. Okay, but I was going to say, can we find disks around other stars, like evidence that other stars are making planets, and find out what those little, asteroids and comets are made of? So as an astronomer, the galaxy is my laboratory. I have to go and look for examples of what I want to find amongst other nearby stars. And this whole field of finding the material that forms planets, the disks around other stars, started with a wonderfully serendipitous discovery. So there was a satellite launched called the Infrared Astronomical Satellite. And its job was to survey the entire sky at infrared wavelengths. And we'll come back and talk more about what the infrared can tell us in a little while. And so it wasn't looking just at any one particular star or any one particular other galaxy. It was doing a survey of the entire sky. But one of the first stars that it returned data on is the star Vega. So if you're an amateur astronomer, you'll know that Vega is one of the brightest stars, naked eye stars in our night sky. You can see it tonight. I'll show you a chart in a minute, but this is Vega in the constellation Lyra. And this is the summer cross here, the swan, Cygnus the swan. So Vega has long been used just as a calibrator star. We know exactly how bright it is, and so we can compare other stars to the brightness of Vega and say how bright they are too. So this new satellite looking in the infrared was intending also to use Vega as a calibrator. And we can look at how bright Vega is in visible wavelengths. So this is a plot that shows you how bright we expect the star to be as a function of wavelengths. So visible wavelengths are those you can see with your eye, about 500 nanometers. Infrared wavelengths are those longer than about 1,000 nanometers, where your eye is no longer sensitive to the light, but there's plenty of light out there that comes from things that are warm or hot. So these are actual measurements of Vega in the blue circles, and this is a model of what how much light the star Vega puts out at every wavelength. So we thought we got Vega, like we understand it. Well, this is a picture of the infrared astronomical satellite. What did it measure? Well, so out here in the infrared, this point looked about right. That was about what people expected from Vega. This next one looked a little bit high. That was a little bit disturbing. And then these were way, way higher than people expected Vega to be based on our understanding of stars, which is actually very good. And the way I heard the story, because one of my advisors in graduate school was one of the investigators on this mission, is that they really were worried when they saw these data come back for the first day. They thought, oh no, something is wrong with our instrument. Probably what's happening is we're leaking light where the star is really bright into our observations at these longer wavelengths. And we've just spent 5 years building this telescope, and now all of our work has been compromised by the fact that we've clearly made some horrible mistake and things aren't working. But then they looked at some other stars and they all looked fine. And they came back and looked at Vega and it still looked weird. And they looked at a lot more stars and they all looked fine. And then they found 3 other stars that were like Vega and showing too much infrared light. And they realized that this was not a problem with the telescope. This was the first discovery of the dust created by asteroids and comets around another star. And that dust doesn't just reflect light to us like mirrors, like we saw in that picture of the Zodiacal Light. It also heats up in the light of the star and it gets warm. And anything warm radiates infrared light. And so what they had found was dust that had warmed up in the starlight of the star Vega and was shining at us, telling us that there is a planetary system around the star Vega. And so you can imagine that they went from being very sad to very happy in the space of just a few days when they figured out what was going on. So this is the best image we have of that dust disk around Vega. It doesn't look very impressive because we're looking at it exactly face on, as if you were holding up a plate and looking at it straight on. So the star is not seen here, but this is all this color. So this is a false color image where red means there's more infrared light, all the way down to blue and purple is the least infrared light. But all the colors that you see here are light coming from the dust around Vega. So it's amazing, right? You can find these tiny little dust grains that are smaller than your hair, and you can find them around another star, and they tell you that that star has made at least comets and asteroids, if not planets. I just find that amazing. And so I like to go outside and have a look at Vega whenever it's up, which it is tonight. So the next clear night, you can go outside. It'll be almost overhead. Sorry, this came out a little small, but you can download a sky chart this one is from OrionTelescopes.com. There are lots of free star charts out, and you can actually go outside and look at Vega right overhead tonight and think about the fact that even though the light that you see doesn't tell you that there's a planetary system there, other kinds of light that astronomers can measure do tell you that there are asteroids and comets around that star. Okay, so that is what we call a disk, that disk of dust around Vega. And I mentioned that it doesn't look very impressive because it's like you're looking at it face on, so it just looks circular. So I like to use the pizza analogy. If you're looking at the pizza face on, you see a disk that's just a circle. But if you're looking at the pizza edge on, or you're watching someone make the pizza spinning it around, you can actually see disks that are at any orientation. So sometimes they look pretty circular. These are all different disks. Sometimes they're tilted, sort of halfway, and then sometimes they're tilted so that they're exactly edge on. And that's both the pleasure and the pain of being an astronomer. We have a whole galaxy of stars to look at, but we have to take what nature gives us. And so sometimes, just by chance, the disks are going to be face on and they're going to look circular. And sometimes, just by chance, they're going to be edge on and look like kind of like a line. And we have to go out and find enough examples that we can try to understand what the intrinsic disk looks like, what that planetary system might look like, independent of how we just happen to be allowed to see it. So I like to think about the study of planet formation as the study of looking at a population of disks. So we want to find the youngest disks and see what they look like and what they're made out of and what compositions they might be delivering to planets. Then we want to look at slightly older disks and see how they've changed, and yet even the oldest ones to see fully formed planetary systems like ours. So it's a little bit like looking at kids, right? No two kids at any given age are alike, but if you look at a couple of kids who are a few months old, they share some similarities. They tend to have chubby cheeks, and they, might have, strange expressions. But they're also different. Some have more hair than others. Some have different colored eyes, right? So they're just as in children, there's natural variation in the young objects that we look at that are forming planets. But if we can look at them when they're babies, and then we can look at a different set of disks, right? Because we can't wait for them to get older, because I'd be waiting 100 million years, and I don't have that long to sit around, but we can look at a selection of kids who are a little older and look at their similarities and try to figure out how planet formation changes over time. So I'll just show you a couple more kinds of things that we can do for finding planets in formation. So this is an image of the disk. Again, it's face on, right, circular, that I made with the Hubble Space Telescope quite a while ago now, before all of you were born, probably. And it is the youngest, closest star to the sun that is still making planets. Its name is TW Hydra, so it's in the constellation Hydra. And we now think that we see actual evidence in this disk of planets, because when you look really closely, and these are our more recent images from the Hubble Space Telescope, you see that the disk is not smooth, but it has these kind of cavities that are carved in it. There's one out here, but there's also one in the center. And in fact, even when you look at this disk even closer, just right in the central area with a telescope called ALMA, which is in Chile, then you see that there are multiple of these gaps that have been carved. And we think that each one of those might be associated with a planet. Sometimes one planet can make multiple gaps, but that there's something in that disk carving out the dust and making planets. So if we could actually eventually find the planets in this disk, that would be perfect, because then we'd be able to study the composition of the asteroids and comets that are going into the planets, and we'd be able to find out about what the planets are like themselves. So this is a challenge that I hope that we'll be able to accomplish in my career, is maybe finding the actual planets that sit inside this disk. We have actually found planets in a disk. Here you can't see the disk so well, but this is a different disk. It's called Lick Calcium 15. This is actually the dust in the disk, although this image was not primarily made to show the disk. It was primarily made to show these little points of light that are in there. So these are not Earth-like planets. They're planets that are bigger than Jupiter. But we do actually know now of a few planets that are in systems that have disks. So we've been able to take the baby pictures of the planets while they're actually forming. And this one actually looks blue here because it is sucking in gas, and that gas is getting really hot as gravity collects it onto the planet, and it's emitting that hydrogen gas is lit up, and that's what makes this planet look blue. So I am going to stop there and see if there are any questions about part one of the talk, and then I'm going to talk a little bit more about how we actually do astronomy as astronomers and what I like about the process of doing astronomy and working at the observatory. But are there any questions on that part so far?
Yes. So how many disks around other stars do we know of?
So if we're talking about the youngest disks, the ones that are still capable of making like Jupiter mass planets, we know of thousands of them. I would say at least several thousand, possibly even 10,000. If we're talking about disks like our own that are just the very faint remnants of the collisions and evaporations of comets and asteroids, then the number is much smaller. It's more like 10 to 100, depending on how you define what a disk like ours is. So those are much harder to find because there's much less stuff in them.
All right. And is there any way to reliably tell if the space telescope is problematic, like if you're getting the wrong readings or not?
Yes, I mean, that's something we worry about all the time when we do experiments. Any scientist worries about, are we making a mistake in some way? And usually the best way to test is to try measuring a lot of different objects or a lot of different stars where, we understand those stars pretty well. And so if the vast majority of observations, look consistent with each other, like if you measure two stars that are supposed to be the same brightness and they come out to be the same brightness, or are supposed to have the same amount of light at different wavelengths and they come out to have the same amount of light, then you think like, okay, like everything's working the way that I think it is. And so this oddball is probably a discovery and not a mistake. But we always face that when we look for disks too, because disks are really faint compared to their stars. So I'll show you in a minute about how some ways that we look for disks, but we always worry, like, what if we just haven't gotten rid of the starlight correctly? Like, is there really a disk there? Or have we just not removed the starlight perfectly? And so we do those kinds of tests. Well, let's remove the starlight from this star. Let's remove the starlight from this star. Let's try this one. Okay, none of those show disks, so probably this one, we did correctly and it's real. But we're always having to do those tests.
Have you ever found an exoplanet, and like out of how many disks that you've looked at, how many had exoplanets?
Well, yeah. So the of the disks that I've looked at, the only ones that we've actually imaged are these. So I guess that's one out of probably the hundreds of disks that I've looked at. On the other hand, almost every disk that we look at looks like this. It has these gaps and rings sometimes and blobs. And so in almost every disk, we think we see evidence for planets. And we're usually trying to convince ourselves, well, could it be caused by something else, or does it really have to be a planet? Like, until you actually see the planet, you're always a little suspicious. Like maybe these rings are caused by a place where you just formed asteroids, but you didn't actually form a full planet. Or maybe these rings are caused by a place where you have a lot more ice. And so the bright parts, you have more ice, and the faint parts, you have less ice. So there are other ways that we can think of making rings, but the best way that we can think of is planets. And because now there are so many planets known around other stars, and we know that planets are common, it's more tempting to invoke planets than other things that are harder to understand because we know planets are common.
All right. Speaking of exoplanets, have you ever found an exoplanet with your team?
Yes. In fact, I think we're about to submit a paper today discovering an exoplanet around a very nearby star. What's exciting about the exoplanet that we think we found is that it's pretty big. It's Jupiter-sized, but it's around a really tiny star, a star that is only 1/10 the mass of the sun. And so it's hard to understand how planets like that form, because generally very low mass stars don't have a lot of disk material around them. And so we think it would be very hard for them to form big planets. And so we've been so it's always fun to find the oddballs because they challenge your ideas of how planets form. And so we've been doing a search for massive planets around really small stars to see whether nature has figured out a way to make them. And nature has, apparently. So now we just have to catch up and think of how that actually happened.
All right. And what is the one most important prerequisite for a planet to sustain life?
I don't know that we know the answer to that question. That's a great question. And that is something that astronomers and geologists are arguing about all the time. I mean, I think everyone would say water, that it's really hard to understand how you could have life without water. On the other hand, you don't want too much water, because if you have an ocean planet, that might create too much water vapor and too much pressure and be crushingly big. But on the other hand, you might need to have enough water. On the other hand, you also have to have land, because it seems to be like geologically the interaction of land and water were important. And so this is where astronomers and geologists need to talk to each other to understand all the things that were important about the Earth. Like, we have a lot going on, right? We have plate tectonics, we have volcanoes, we have a core with a magnetic field that protects the Earth from charged particles. Like, there are a lot of possible aspects of the Earth that make it a good place for life. And it might be that they're all important. Like, if we didn't have them all together, then life would be extremely difficult to sustain on Earth, even if it could form.
For sure, yeah. And that brings us to our next question. Theoretically, couldn't any planet be habitable but just have a different type of life form that's adapted to that specific planet? And if other types of life can exist that do not require the same conditions on Earth, why do we focus on finding life similar to that of Earth?
Right. Well, that's a really good question. It's the best reason to look for life like ours is that at least we have an existence proof, right? The only life we know about is here on Earth, and it all works on the same physical processes, right? DNA or RNA is the genetic code for all life on Earth. And all life on Earth requires water. All life on Earth is primarily composed of carbon, hydrogen, oxygen, nitrogen, and sulfur. All life needs an energy source, right? So you're right. Like, people have tried to dream up completely different forms of life, but it's really hard to look for something that you don't know anything about. So, because you have to design experiments as scientists, you have to say, is something on that planet or not, right? So is there oxygen on that planet or not? Oxygen in our atmosphere is evidence of life on Earth. There was no oxygen in the first 2 billion years of Earth's history. There was essentially no oxygen in the atmosphere. It was life that created all the oxygen in the atmosphere. So a lot of what astronomers talk about in terms of looking for life is looking for two things together that naturally shouldn't be there. So for example, volcanoes on Earth put out methane gas, and methane reacts really strongly with oxygen. So you might expect the methane from volcanoes to destroy the oxygen in an atmosphere. And yet the Earth has a lot of oxygen. Well, that's because life is constantly making more oxygen. So one way we think about looking for life is looking for two things found at the same time that wouldn't be there naturally, that would require life in order to produce them. And so then it doesn't tell you, you don't have to rely on understanding DNA or RNA or cells or any of the mechanisms of life. You're just trying to think about things that life would throw out of balance, that it would make a planet look abnormal compared to how it would look otherwise.
Okay. I'm afraid we've had a lot of questions for part one, but just for the sake of time, I think we need to move on to part two.
Yeah, let's talk a little bit about part two, and I'll try to go through this quickly so we have plenty of time for more questions. But I wanted to tell you a little bit about how we do astronomy. I'm sitting with this picture of our observatory in the background. So the whole point of astronomy is to use light, because that's essentially the only messenger we have from the stars or from the universe. Gravitational waves are another messenger you might have heard of recently. But mostly what astronomers do is look for light. And light is any kind of electromagnetic radiation. So it goes all the way from the radio, which we normally think of as a communication technique, but that image that I showed you from the ALMA telescope was a radio telescope image. The infrared, my favorite, because I grew up as an infrared astronomer, so that's a picture of me in the infrared. The visible, of course, that we're most familiar with, and the first kind of astronomy ever done was done in the visible. But you can also do astronomy in the X-ray and in the gamma ray. They don't get through the Earth's atmosphere, and most infrared doesn't get through the Earth's atmosphere. So to do a lot of the wavelengths of light, we have to have telescopes in space. For parts of the infrared, parts of the radio, and in the visible, we can do astronomy from the ground. So we build telescopes in both places because we want to measure all those different kinds of light. So this is just a collage of all the telescopes I think I've ever used. Maybe I'm missing some. This one is my telescope that I got when I was 13 years old. It's an Edmund Astroscan. They don't make it anymore. It's 4¼ inch mirror, but I love it. And these are my kids. And this is us looking at the lunar eclipse about 3 years ago. And this is just last year, we were watching the transit of Mercury across the face of the sun. So Mercury went between us and the sun, and it blocked some of the light of the sun. So that's just like how we find exoplanets. We can find Mercury that way. So this is my son, who's a high school senior, and I were in the backyard observing the transit of Mercury with my little telescope. But this is a giant radio telescope in Green Bank, West Virginia. You can actually stand on the telescope because radio telescopes aren't so fragile. This is the ALMA telescope in the high Atacama Desert in Chile. This is a telescope on an airplane called Sophia. So if you can't launch a telescope into space, the next best thing is to get above as much of the Earth's atmosphere as possible. So there I am about to get onto the airplane. And when the airplane flies, it opens a door in the side and the telescope looks out. You're in a pressurized part of the plane, so you have to carry oxygen with you, but you don't have to, actually wear a mask all the time. So these are some ground-based telescopes. I'll show you more in a minute that work mostly at optical and near infrared wavelengths. This is the Keck telescope, which is the biggest telescope in the world on Mauna Kea in Hawaii. And then, of course, we have the space telescopes. We have the Hubble Space Telescope and the Spitzer Space Telescope here. So I love telescopes. The bigger, the better. But if they're infrared, then that's even better. And these are just some hazards of doing astronomy. So my favorite set of telescopes are the ones that my institution, the Carnegie Institution, owns and operates in the Atacama Desert in Chile. This is a beautiful picture of a meteor shower. So looking at those asteroids coming and hitting the Earth and delivering their materials to us. These are all meteors entering the Earth's atmosphere. And these are the telescopes, which are not looking at the meteor shower. They're looking at whatever other things people were doing that night. So when I go to the telescope, I have to fly down to Chile. Our observatory has been closed, like most other things, because of the COVID pandemic since March. So I usually go a couple times a year. So our observatory is a couple hundred miles north of the capital of Chile, which is Santiago there. And it takes about 24 hours to get there. So it's not the most fun trip, but it's a really beautiful place. You can see it's in the desert. There's not a lot of stuff growing here. And that's obviously because most of the time we want clear skies, right? We don't want clouds. There's really great wildlife. This is a guanaco, which is related to a llama. There's one in the picture behind me, actually, if you can see right there, there's a guanaco. And this is a vizcacha, which is kind of looks like a cross between a rabbit and a squirrel. They're super cute, and they've discovered that humans like them, so they tend to hang out near the astronomers. So I made this little movie that shows a little bit what it's like to observe on a large telescope. And this was a time when we were commissioning a new instrument in the telescope. And so we had a huge team of people there. You can see there were like 5 or 6 people there, which is not usual. Sometimes I'm there observing more or less by myself. There's always a telescope operator. That's Hector, the telescope operator. The telescopes are too precious to be left in the hands of astronomers. We might be like, well, it's only raining a little bit. Like, we'll just keep it open. So he's there to protect the telescope and fix things if they break and point where we tell him to go. The astronomer's job is to use the telescope and the instruments to do the science that they want to do. And so there's the telescope operator. He manages all those different screens that tell him how the telescope is working. And the astronomers use the screens that tell them how the instruments are working. And so we never actually go out and look through the telescope with our eyes, because our eyes, while they were great for doing astronomy when we didn't have digital cameras, our digital cameras are way more sensitive to light and better at looking at things than our eyes. So that night we were commissioning the instrument that lets us make images of disks and planets. And the way it does that is by correcting the effects of the Earth's atmosphere. So here's an example of what a star looks like through the Earth's atmosphere. These fuzzy blobs, stars should be just points of light, but they all look like fuzzy blobs because of the Earth's atmosphere. So the idea of adaptive optics is to take that fuzzy blob and correct it as if it would look if you were outside the Earth's atmosphere. Oops. Movie didn't play there. So what we do is we use the light, and then we try to remove the effects of the atmosphere, and you get back images that look like this, where almost all the light is put into a single point. And actually circular telescopes always make images that have rings. That's the diffraction of the optics of the telescope. So we can turn the star into a point of light, and then that lets us see what's around it. Or in this case, you can see that this star is actually 2 stars, right? Which we're able to see very well once we correct for the Earth's atmosphere. So the telescopes of the future, and this is the world's largest telescope that's being built at our observatory right now to be done in about a decade, it will use that kind of technique to correct for the Earth's atmosphere, and it will be about 10 times as big as any telescope ever launched into space. And so that means it can see 10 times more detail on disks or look for planets around other stars than even a telescope in space can. I showed you the pictures of Sophia, so we can use telescopes off the ground. And of course, we can use telescopes in space. So this is the Hubble Space Telescope, but NASA is going to launch the James Webb Space Telescope in about 1.5 years, hopefully. And it'll be the largest telescope in space, but this is only this is the same size as our telescopes in Chile, the Magellan telescopes. But it'll be the biggest telescope ever launched into space because it's so much harder to launch a big telescope into space than it is to build one on the ground. So we've had telescopes bigger than this on the ground for 30 years, right? But it's much, much harder to launch and more expensive. Okay, and then I wanted to talk about why I love the infrared so much. So these are 2 pictures of a constellation that you might recognize, known as Orion. And if you look at Orion in the visible, you can see this sword, the sword of Orion, is kind of a fuzzy patch with your eye or with a small telescope or binoculars. And if you look at Orion in the infrared, so this is an image taken with that same satellite that discovered the first dust around Vega, then that sword is actually the brightest infrared object in the entire sky. And what it actually is a place where young stars are forming. There are 10,000 young stars there, all shrouded in dust, and they're heating up that dust, just like stars like Vega heat up their dust, and that dust is glowing in the infrared. So whenever you see really bright glowing infrared, that usually tells you that there are stars and planets in formation there. And it's easier for infrared light to get to us through dust. And so it's a great probe of those places. So just like the sunset looks red because it's easier for the red light to get to us from the sun through all the Earth's atmosphere than the blue light, things tend to glow in the infrared, even if they're obscured by a lot of dust. So we use infrared on the Earth too. You can buy these little infrared cameras, which I'll turn mine on here so I can show it to you in a second. So this is actually a firefighter that's hard to see through all the smoke. But if you take a picture of the firefighter in the infrared, you can actually find him through the smoke. And so it's the same idea in space, which is that we look for the infrared to tell us where young stars or things that are warm are that we wouldn't be able to see otherwise. So here is that Orion Nebula, as we call it, that area of gas and dust, as seen if you can peer through all the dust to see the young stars that are forming in there. So this movie was made from a composite of a lot of different Hubble Space Telescope images that were put together to try to give you a sense of what the Orion Nebula would look like. So each of those points of light is a young star. You can see some of them are surrounded by disks. Some of those disks have little tails because the really bright stars in the Orion Nebula are evaporating them. But if you go down and look inside those halos of gas and dust that are being evaporated, then you can see, and this is just the animation part, a disk like the one I showed you around TW Hydra that could be forming planets. And the infrared is the only way we get to see those things. Okay, so I am going to switch here to my infrared camera for a second, and hopefully then we will be able to get a little tour of the infrared in real time. Okay, all right, here we go. So here, all right, there's me today in the infrared. I'm pretty warm. You can see my glasses don't let infrared through, right? So some materials are really still opaque in the infrared. If I take off my glasses, you'll see my eyes are actually pretty hot, right? But the infrared doesn't get through my glasses. The infrared does get through some materials that are opaque. So this is a plastic bag. It's like an ordinary trash bag that I would put in my kitchen trash. And it's actually pretty transparent in the infrared. If I hold it in front of my face, you can see a lot of infrared still gets through it. If you can see me on your screens as well, you can see that that trash bag was completely opaque in the visible, right? But it's not completely opaque in the infrared. You can still see my face. And things that are hotter produce more infrared. This is a false color image. So the white is where I'm hottest and the black is where I'm coolest. But if I look instead at, ooh, I just poured it all over my leg, at a cup of ice here, you can see that that's very cold. So at the bottom where the cup is cold, it's the blackest. And I might even be able to look into the, hard to get that right without pouring all over my leg as I just did. So that's why we use the infrared, because it sees through things and it sees things that are warm. And in particular, young stars and the dust around them are warm. Okay, I'm going to stop sharing. All right, so I will just say one final conclusion and then be happy to take more of your questions. And that is, oh, there's the Vizcacha in the infrared, by the way. To know if a planet is habitable, it's probably not enough to just know what temperature it is and where it is around its star. We need to know what it's made of, how it formed, and how it's evolved since it formed. Does it have the things like plate tectonics and volcanoes and a magnetic field that Earth has? So we have a lot to discover about planets, and I want to encourage all of you to just keep looking up. And now I'm happy to take more of your questions.
Yeah, that was a great presentation. I certainly learned a lot from it. We've had a couple of questions. So how do you differentiate, like you would use the like so for the Mercury transit, you would tell that Mercury is passing by the sun by how, like, the level of light the sun is giving off. So how do you differentiate planets from black spots?
Well, so stars have spots, but they're not black. They're not totally opaque, right? Planets are almost entirely opaque, right? The spots on stars are cooler usually than the surface of the star. Sometimes there can be hot spots. Usually they're cooler, but they're not completely opaque. And the other thing is that spots rotate with the period of the star. So our sun rotates, all stars rotate. The spots come and go at that period, which is different than the period in which the planet is going around. So sometimes you can see two signals, the signal of rotation of the star and the signal of the planet going around the star.
Okay. Yes, so what? For you, what is the end goal for finding Earth-like exoplanets? Like, some people believe we need to colonize other planets to sustain humanity. Some people are just interested in alien life. So,
Yeah, no, I think we better take care of our planet because it's not practical to go to another one. No, for me, the real question is not even finding a twin of the Earth. The question that I'm interested in is, how do planets form and what variety of planets are there out there? Because I just like physics. I like to understand how things work, and how planets form is one of those essential questions to me about how the universe works. And it's a pure curiosity question. It's not going to help anything about our lives other than satisfy our sense of curiosity and wonder. But I do like to think that one of the special things about humans is that we like to wonder and are curious.
yeah, great. I'm afraid we've run out of time. It's already 11 o'clock. So thank you, Dr. Weinberger, for talking to us about habitable planets. It was a really wonderful presentation. I'm sure all of us learned a lot from it. ConnectCon would not have been possible without you or any of our speakers. And thank you to our alumni here, Ishan Oberoi, Sarthak Bhatnagar, Angeline Zhang, and others for their help. Lastly, thank you for our audience for being attentive and kind. We hope to see you again this afternoon. Meenakshi Patel will be talking about emerging technologies and making the leap effective this afternoon at 2 p.m. Thank you all, and see you this afternoon. Dr. Weinberger, do you have anything else to say?
I don't, except that you can find me on Twitter and on the web. And so if you have questions, I'm sure you can look me up and send them to me.
Yeah. So I was just about to say that if you have any questions, you could email it to us and we'll forward it to Dr. Weinberger.
That would be great.
Please make sure to like and subscribe to our YouTube channel, Wizards.exe number 9794. Follow us on Twitter, Instagram, and Facebook, and check out our website if you want to find out about more STEM opportunities like this. Thank you once again to Dr. Alycia Weinberger from all of us here today. And thank you for watching.